In industrial automation, you often need to take a massive amount of kinetic energy, like a multi-ton payload sliding down a track, and bring it to a perfect rigid stop in a fraction of a second. But the command to stop that payload doesn't come from a heavy machine. It comes from a microscopic digital signal operating on just a fraction of a volt inside a control system. Bridging the gap between that delicate computation and immense physical force is the core of mechatronics. It requires a system that can safely translate low-power logic into high-power mechanical action without blowing the fragile electronics to pieces. To see how this works, we are going to reverse engineer an automated system from the ground up. We will start by defining the physical motion, calculate the pneumatic pressure needed to drive it, and finally map the electrical relay circuits that control it. Tracing this sequence of cause and effect is known as the mechatronic action pathway. Mastering it is essential for both real-world engineering and your final exams. Before we can select a motor or a pneumatic cylinder, we have to precisely define the required physical movement using the equations of motion. This chart lists the standard variables used in kinematics: starting velocity u, final velocity v, acceleration a, distance s, and time t. From these variables, we derive two foundational equations, one calculating acceleration as the change in velocity over time, and another calculating distance as average speed multiplied by time. However, we run into a practical problem. In industrial design, you usually know the total distance a machine part has to travel and the target velocity it needs to hit, but you rarely know the exact time duration. We isolate t in both equations. Because both equal t, we set them equal, eliminating time entirely. Cross-multiplying the denominators gives 2as equals v minus u times u plus v. Expanding brackets simplifies to our final equation, v squared minus u squared equals 2as. This formula is the bedrock for sizing mechanical actuators, dictating the necessary acceleration using only the spatial boundaries of the machine itself. We need a pneumatic cylinder to accelerate a 2,000 Newton table. To find the required force, we divide weight by gravity for mass and multiply by target acceleration. Combining this with sliding track friction reveals the cylinder must generate 353 newtons of total force. Knowing the total mechanical force is only half the battle. We now must translate that physical requirement into fluid pressure inside the cylinder. Pressure equals force divided by area. Dividing our 353 newtons by the cross-sectional area of the 50mm cylinder bore reveals that the pressure required to move the table is 1.79 bar. However, operating a machine involves multiple phases of motion, like accelerating and braking. The system must be capable of handling surge pressure, the sum total of pressures from these different forces. Here, combining the acceleration and deceleration requirements yields a surge pressure of 3.75 bar. By calculating these steps, we've mapped an abstract speed requirement to a tangible required volume of compressed air. This brings us to the control layer. How exactly does a delicate, low-voltage computer signal trigger a valve to unleash massive physical pressure? The process begins with a solenoid. As shown here, a solenoid is a coil of wire wound into a tightly packed helix. Passing electric current through it generates a uniform magnetic field, turning the coil into an electromagnet that can physically pull open a pneumatic valve. But we immediately hit a power gap. The tiny electrical currents leaving a computer processor are too weak to power the solenoid directly. To cross this gap, engineers use an electromechanical switch called a relay. A relay allows a sensitive, low-power control signal to switch on a completely separate, high-power circuit. This diagram illustrates an electromagnetic relay, an energizing coil, a pivoting armature, and contacts. A weak signal enters the bottom coil, creating magnetic flux that pulls the armature inward. That mechanical pivot pushes the movable contact upward, closing the secondary circuit to let heavy industrial current flow out. When reading schematics, you will see this physical relationship represented abstractly. The coil symbol, labeled 2, acts as the trigger that mechanically closes the switch symbol, labeled 3. The relay acts as an isolating barrier, allowing delicate digital logic to command massive industrial power without risking electrical feedback that would destroy the computer. Let's trace the entire mechatronic action pathway. It operates as a strict linear sequence of amplification. First, a low-voltage control pulse fires into the relay coil,
which closes the heavy-duty circuit to energize the solenoid electromagnet. Next, the solenoid actuates the main valve, unblocking the path for compressed air to hit the calculated surge pressure. Finally, that localized pressure generates the exact force needed to overcome track friction and drive the payload to the target acceleration, as governed by the equation v² minus u² equals 2as. Mastering the pathway, working backward from the motion requirements on the track to the tiny electrical trigger in the relay, is how you design complex machines and how you conquer systems engineering exams.